Hi, good evening, students. How are you all doing? My name is Sumit Kundu, and I'm a BTech graduate from IIT Bombay. And today we'll be discussing a few problems from a particular section of physics for your KVPY examinations. All right, students. Now, here in my previous videos on optics and thermal physics, the basic idea was to analyze what have been important in KVPY over the previous years, and that's what we have done it for electrodynamics as well. Now, repeatedly over the years, we have seen there are certain questions coming from charging and discharging of capacitors. That means in a circuit, if we have both capacitors and resistors connected in the circuit, then how do we solve those questions in your circuit problems? All right. Now, the basic idea behind solving these questions, my dear students, is very simple. That is, if you have a circuit where you have a capacitor as well as a resistor connected, then, my dear students, in such a case, when we close the switch out here, the capacitor does not get charged instantly. Rather, it takes certain time to be fully charged. That is the entire idea. Now, there are two instances that we need to look at. All right, students, what are the two instances? The first instance, that is just after closing the switch. What is happening just after closing the switch? At that instant, the charges have not yet developed across the capacitor. Now, if charges have not developed across the capacitor, then potential difference, my dear students, across the capacitor is equal to 0. Then we can technically replace this capacitor in the circuit by a straight wire. In the place of the capacitor, we just have a straight wire out here. All right. And the current in the circuit is given by the simple Ohm's law equation, that is I is equals to V upon R. Now, that is the basic idea. Just after closing the switch, what is happening? We just replace all the capacitors or in the branches that has a capacitor by a simple straight wire. That is the idea. First idea. The second idea. After a very long time, what is going to happen? After a very long time, my capacitor, students, right, is going to get fully charged. Now, if my capacitor gets fully charged, then the branch which will contain the capacitor, my dear students, what is going to happen to that? Then no current is going to flow through that particular branch. So here, if I see that my capacitor gets fully charged, then through that branch, my current flowing is going to be equal to 0. Then the potential difference across the resistor will also be equal to 0, students. Then the potential difference across the capacitor, as you can see, will be equal to the EMF of the cell. So that's the basic idea which we are going to use to solve so many different kinds of problems in our today's session, guys. Okay, so here let's take up the first problem. In my first problem, this is a very simple circuit that has been shown out here. I have got 3 resistors. If you can check them out, these are my 3 resistors, along with I have a capacitor. Okay, now we are taking the simple 2 cases. We want to find out the values of I1, I2 and I3. Okay, students, for 2 cases. Number 1, just after the circuit is closed, that is when I kind of plug on this switch out here, and after a very long time. Okay, and it has been mentioned to us that my capacitor is initially discharged or uncharged. All right, so what did we say? In the basic idea behind this, just after the switch is closed, the basic idea is I can replace my capacitor by a straight wire. So I have to imagine that there is no capacitor at all out here. Okay, then students, it's such a simple problem if you would see. Okay, the current out here, this and this would be in parallel. So their equivalent resistance is going to be R by 2, which is in series with this R. All right. So the net resistance of the circuit is going to be nothing but R equivalent will be equals to 3R by 2, my dear students. Okay, then what will be the current drawn from the battery or from the cell? The current drawn from the cell will be equals to I is equals to V divided by R equivalent. So students, that would be 3R, and in the numerator I'm going to have 2. All right, students. Now that is going to be the current given by the cell or the battery, students. Okay, so what is going to be the value of my I1? That is exactly the current provided by the cell. All right, so that is going to be 2V upon 3R. Okay, guys. Now the next thing about I2 and I3. Both these branches are kind of identical. If you see, both these branches have the same resistance, that is equal to R. So what is going to be the current flowing through each of them? The current is going to get equally divided between them. So if they get equally divided, then I can say my I2 will be equal to I3, all right? And that is going to be nothing but V divided by 3R. All right, students. So that's the basic idea or the first concept that we have used here. And I think you will find it that it's pretty simple. Okay. Now, as we go ahead, students, what are we going to do? We are going to take up some questions from KVPY. All right. And see, like, they have repeatedly come over the previous years in 2012, 2013, 2014. All right. And a very similar connected problem in 2015 as well. All right. So over these years, every year there was a question on this basic simple idea that if I have my resistor and capacitor both connected in the circuit. Okay. Now, students, next thing, what is going to happen after a very long time? See, after a very long time, we say that it's a steady state has been reached. My capacitor has become now fully charged. Now, if my capacitor has become fully charged, okay, is there any current going to flow through that? No. Then in that case, my dear students, after a very long time, my I3, if you observe here, my I3 will become equal to 0, my dear students. Okay, my I3 will technically become equal to 0. All right. What about my I1 and I2? That's even simpler now. Now these are nothing but they are in series. If you can look at them, then the equivalent resistance of the circuit after a long time, if you would say, my I1 will be equal to I2, that will be equal to nothing but V divided by 2R. That's the result that we are going to get after a very long time, students. All right. Did you enjoy this problem? Very basic, very simple. All right. Let's go to the next one. All right. Fine. So that's a blank slide we have here. Okay. So we'll take up this question right now. Now let us understand what is the premise of this particular question that we have out here. Okay, students. Now here what they are saying is, that is my switch 1 remains closed for a long time. So initially I have this part of the circuit which is kind of active. All right. So it's on for a very long time. What does it mean, my dear students? It means that my capacitor has become fully charged. Now, if my capacitor has become fully charged, all right, students, what would it say actually? If my capacitor is like fully charged, then the potential difference across the capacitor would be equal to V. All right, students. Now, what they are doing is, now S2 is closed and S1 is open. So they have kind of closed S2 and they have opened my S1. All right. So now in the second part of the circuit, what has happened in the second part? In the second part, my left portion of the circuit has deactivated and the right portion of the circuit has become activated. So this is my circuit that is kind of active as of now. Okay, students. Now, what is the question asked to us? Find out the current in the capacitor just after this moment and the charge on the capacitor after a long time. Okay. Now, going ahead, my dear students, what do we see? Now, here the potential difference initially will be equals to V. Now, when I close S2 and kind of open my S1, what is going to happen? Then see, once we had it like, steady state has been reached, current was 0. Clear? But now when you close S2, right, students, and you open your S1 out here, right? Then what is going to happen? What do we see? The potential difference across the capacitor will remain as V only, right? So what we'll do is to find out the current, that's what they have asked us out here. To find out the current, we are going to apply your KVL, Kirchhoff's voltage law. Okay. Now, when we apply it to this circuit like A, B, C, and D, then what do we see here? That as it is going up, it is plus V, negative terminal to positive terminal. Okay. The potential drop across the resistor is going to be how much? 2IR, because we are assuming I current is flowing in the circuit. All right. And here it is again going from the negative terminal to the positive terminal. So there is a potential rise. So we take it as positive, my dear students. So that's like 2V is equal to 0. If we calculate, we get a simple solution, that is my I is equals to 3V by 2R. All right, students. And next thing, what is going to be the charge on the capacitor after a long time? After a long time, what is going to happen, my dear students? All right. After a very long time, the capacitance ke across, whatever is the potential difference, it is going to become equals to 2V. All right. Then the charge on the capacitor plates is going to be how much? C into 2V. Because we know Q is equals to what? CV. Isn't it, students? See, now here the potential difference has become 2V. So this will become C into 2V. That is going to be the charge across the capacitor, students. All right. Now, we'll take up another problem, a very simple one. The idea, the basic idea is same for all these questions. All right. Now, this is one question. Again, it's on a very simple concept that we have just studied in today's session, students. You see this? This is a battery here, 2 ohm resistor, 4 ohm resistor, 6 ohm resistor. They are all connected out here, and we have got a capacitor as well. That is 2 microfarad. We need to find out the charge on the capacitor in a steady state condition. Steady state condition means that it has been charged for a very long time. So it's like fully charged. So if it is like fully charged, my dear students, what is going to happen? The idea is very simple. The current in the circuit, as you would say, there is going to be no current flowing through this branch. Clear? Since it is like fully charged. Okay. Then what is going to be the current in the circuit? Then I take the outer loop out here and my current becomes 12 divided by this 2 and 6 are in series. So that is like 1.5 ampere, students. Then students, what will be the voltage drop across this? It's going to be I into R, that is 2 into 1.5, that is 3 volt. Then what will be the potential difference across these two ends? It is going to be nothing but 12 minus 3 volts. That means it is going to be 9 volts. If I name this as like A and this as B, then I can say my VAB is nothing but equals to 12 minus 3, that is 9 volts. Okay. Then what will be the potential difference across these 2 points? 9 volts. Absolutely correct. Okay. Is there any potential difference across the 4 ohm resistor? No, there is no potential difference across the 4 ohm resistor. Why? Because there is no current flowing in that branch. All right. So the potential difference across these 2 points, C and D, let's say, that also is going to be equal to 9 volts. All right, students. Then that is the potential difference across the capacitor. That is 9 volts. And if you have to find out the charge on the capacitor during that time, very simple. Q is equals to CV. You apply that formula, you get your value as 18 microcoulomb, students. Okay. So we are repeating the same concept in all the questions. All right. Now here, using the same concept, now we are going to do what? Is we are going to look at 1 or 2 questions from KVPY. And I have another genre of questions for you. That is, if we reverse the polarity of the battery, what happens? Okay, how much heat is produced in the circuit? Or let's say I do not change the polarity, but I decrease the EMF of the battery. Okay, so in that particular case, what is going to happen? Okay, so here we are going to look at few questions from KVPY now, and after that, students, after that we are going to look at the reversing of the polarity and changing the EMF of the cell. Okay, now here this is one question we had it for KVPY 2003 year. All right, so right away let's get to the solution of this, students. Aja. Some students say that we need to find out what? We need to find out the charge stored, all right, in the capacitor once it is like fully charged. Now, certain people, they have the idea like, this is like a R by R and R by R. Okay, so that's like, a balanced Wheatstone condition. So potential difference across this is going to be zero. So charge stored also is going to be zero. Students, that's a wrong answer. Clear? We technically need to solve this circuit in order to get to the problem. Okay, now here, what we understand from here is these two are basically in series. All right, students. So the net equivalent resistance becomes equals to 2R. Now with this 2R, if you see, this R is in parallel. Clear? So 2R and another R. So how much would it become basically? That would be becoming nothing but 2R by 3. All right. And after that, if you see across these two ends, this R is connected in series with this entire combination across these two ends. Clear? That means I have my net equivalent resistance across point A and point B equals to 2R by 3 plus R. Then students, what is the net equivalent resistance? It is nothing but 5R. All right. It is nothing but equals to 5R divided by 3. Okay, students. Then I can have this entire circuit being redrawn in a way that I have here my resistance R. Clear? Here again I have another resistance R. Between this I have my capacitor being placed. All right, students. Here I have the EMF, the battery being connected. And here then I have a fully equivalent resistance, all right, of 5R by 3. This is R and this is R. Okay, students, and this is V. So this is how I would simplify my circuit diagram so far. Clear, students? Now, going ahead, if you would see, let's say current I comes out of this battery. All right. And from here, I1 is flowing. And through this, I2 is flowing. There's no current that is going to enter the capacitor. Why, students? Because it's like fully charged. Because I mean, like, it's that's the state that is given to us, that it is fully charged out here. Then, my dear students, I can apply the KVL in this loop here, like A, B, C, D, and A. Then, students, if I do that, what will I get? V minus I1 into R minus I1 into 5R by 3, okay, is equal to 0. All right, students, what will I get here? I'll get 8 I1, okay, R upon 3. Is this clear to everyone, students? Very simple so far. Then, what do I observe? That is, my I1 is equal to 3V upon 8R. Right, students? Then, in this particular problem, if you see what is the potential, we need to find out the charge stored across the capacitor. Okay, then whatever is the potential difference across the resistor is the potential difference across the capacitor also. Now, what is the potential difference across this particular resistor? If you see, it is nothing but I1 into 5R by 3. Then the potential difference across the capacitor will also be the same. That is going to be I1 into 5R upon 3. Okay, students. Then what is my I1 out here? It is nothing but 3V by 8R. Clear? You kind of multiply it with 5R by 3. Alright, students. What do I get here? R and R is going to cancel, 3 and 3 is going to cancel. So I have got it as 5V upon 8. Clear, students? Then I think you must have already guessed it. What is the charge stored in the capacitor? This is the answer here. That is 5 by 8 into CV is the charge stored in the capacitor once it is like fully charged. Okay, guys. Now, based on the same concept, we will see 2 more questions and then we will go to reversing the polarity of the battery. Okay, students? Okay, fine. So now, as we would see here, I would want mostly that the next 2 questions, why don't you people solve? Like, shouldn't it be the focus of our today's session? That is, we learn something and on the basis of that, you're able to solve questions of KVPY of your previous years. All right. And I'm sure, students, once you do that, you will feel much confident and much motivated. Okay. Just excuse me for 2 minutes. Now, here, going ahead, what do we see here is the next question. All right. Now, in the next question, students, I think it's a very simple one. I've just made it like a little solving out here. In the previous case also, this has appeared again in the year 2013. So you see in the year 2013, there were like 2 questions from your RC circuits in your examination. Okay. Now, the first one, I know it would have taken some time. It was not that easy. All right. Imagining it. But the second question, if you see, it's kind of very, very easy. So for the third question, okay, third question, you people do it on your own. Let's stick to the second one. Now, in the second one, okay, if it is connected for a very long time, then students, the idea is very simple. If it's kind of connected for a very long time, I through this is going to be equal to 0. Okay, then we have just this circuit out here. Clear? Then this is going to be like, I'll just rub this out here. Clear? And also this. The question is simple, students. I know that we can even go ahead, skip it and go ahead if you want to. That's just the idea which is out here. I is going to be nothing but 6 volts divided by 3 kilo. So 3 into 10 to the power 3. Okay. And that is going to give me 2 into 10 to the power minus 3 ampere. So that's like 2 milliampere. And we have to find out what is the voltage across the capacitor. See, the voltage across the capacitor, if you find out, it's nothing but this. And since there is no current flowing through this branch, then my dear students, voltage across the capacitor is same as voltage across these 2 points. Okay. Repeating it once again, whatever is the voltage across these 2 points is the voltage across these 2 points. Okay. Then my dear, very simple, voltage across the capacitor is going to be I into 2 kilovolts. Okay, sorry, 2 kilo ohms. Then I is equal to what, my dear students? Just calculate it. You will get your answer as 4 volts. Okay, very simple. You get 1 marks for this, 2013. Okay, so that's like a very lollipop questions for all of you. Okay, guys. Next question, students, I leave it to you. I'll give you some time to just take a note of this question, okay? And let's interact, okay, over our WhatsApp. We do a lot over the Vedantu. The students interact with us over the WhatsApp, sharing questions and answers and solutions. That keeps on happening, like, day in and day out. So here I have my phone number being given to you. Kindly take a note of it. 83088070045. My students, this is my WhatsApp number, and I would request that once you have taken a note of this question, you can just send me, like, what is the option, like, A, B, C. You don't have to, like, give the entire solution. If you have solved it on a piece of paper, you can take a photograph of the same and just, like, kind of upload it as a pic to this particular WhatsApp number out here, students. Okay, so let me see how many of you have understood the concept and has been able to do this question, which has appeared in the year 2014 for your KVPY. Okay, so students, that's like one genre of questions we've just finished out here. All right, and now what we are going to do is, like, look at another set, a similar kind of problem, okay, which has appeared in the previous years. So let's get all well acquainted with this. And it's a popular concept even for your JEE examinations. Okay. Now, here in this question, what we are looking at, that we have a capacitor, right? And that kind of is, like, fully charged. We have this capacitor here that is, like, fully charged, disconnected to a battery, which has got an EMF of V volts. And we have a resistor out here. Okay, students. Now, what they do is they disconnect the battery and they reconnect it by reversing the polarity of the battery. Okay. Now, after steady state is being reached once again, they want us to know how much is the heat produced in this particular case. Okay. So, like, this is now fully charged. Okay. Disconnect the battery. Step number 1. Reverse its polarity. Step number 2, guys. And third is reconnect it again. All right. So that's, like, first charging starts again, and then it's, like, fully charged. So these are the 3 things that we have out here. All right, students. Now, what is the idea behind the entire question? Let me just share with you first. We need to work. This is what is the formula that we need to keep in mind. Okay, students. That is a work done by the battery. All right, because who's the energy provider in the circuit? The energy provider in the circuit is definitely the cell, the battery. All right, so whatever energy is being provided by the battery, that is basically the work done by the battery, students. It is nothing but equals to, it is the change in the energy stored in the capacitor plus whatever is the heat produced. All right, so whatever energy is being provided, my dear students, by the cell or the battery, it does 2 things. It changes the energy in the capacitor, and second thing is heat gets dissipated across the resistor, all right, or the flowing wires, and if it's an ideal wire, then only across the resistor. Okay, students. Now, if you would see, this B had initial charge of how much? So the charge, my dear students, if you see, I'll take to this. So the charge on plate B is minus CV. So the charge on plate B initially is equals to minus CV. And after I have disconnected, reconnected the charge, finally, if you would see this, it has become charge on plate B finally is plus CV. So, my dear students, tell me something, how much amount of charge has to be pumped by the cell in order to gain this particular charge, all right, or this particular configuration? So the charge provided by the battery will be equals to charge final minus the charge initial. All right, students. So that is nothing but equals to 2 CV. All right. So 2 CV amount of charge has been pumped by the cell into the circuit right now after the reversing has taken place. Okay. Now in that particular case, I see the work done by the battery is going to be what? It is nothing but 2 CV. That is the charge which is being pumped by the cell. All right. And across how much potential difference? If you would see here, the current goes this way after you have reversed it. Okay. So once you have reversed it, it is going from negative to positive. All right. So how much work is being done by the battery? Very simple. It is charge transferred into the potential difference across which it has been transferred. So that is like 2 CV square. All right, students. Fine. Now, what is this? This is like, my dear students, 2CV square, and that is equal to, my dear students, change in energy stored in the battery. Okay, now change in energy stored in the battery, students, is equal to what? Final energy stored in the capacitor. Sorry, change in energy stored in the capacitor. So final energy stored in the capacitor minus the initial energy stored in the capacitor. Okay, what is the final energy stored in the capacitor? If you would see, this is like UF, all right, minus U initial. Clear, students? Plus whatever is the heat that was generated. So that's like Q. Okay. Now let's get back to the circuit once again. Not this one here. Initially, it is half CV square, my dear students. This is my U initial. And if you see, this is my final situation where the charging has actually stopped. All right. So what is my U final equals to? Any guesses? All of you? Any guesses? Yeah, it is half CV square. So has there been any change in the energy stored in the capacitor? No. The change in the energy stored in the capacitor is basically equal to 0. So if I kind of put it out here, this is 0, then the heat produced, yes, my dear students, the heat produced is going to be equal to 2CV squared. All right. So that's the basic idea behind the entire question out here. You calculate what was the initial charge, you calculate what is the final charge, and then you apply the equation that whatever is the work done by the battery, this is the entire key thought behind these questions. That is, whatever is the work done by the battery, it is going to go in 2 ways. One, change in energy across the capacitor, and second thing, whatever is the heat dissipated across the resistors or the external wires. All right, students. Fine, students. So with the same thought, I'm going to do one more question with you, and that would be all for our today's session. Okay, you can always reply back to me at my WhatsApp number, and also leave a message in the comment section telling me how did you like today's session. All right, and if there is something else that you would like to study through me in our online sessions out here. Okay, guys. Now, here we are not going to reverse the polarity, students. Idea is very clear. We are not going to reverse the polarity. What we are going to do out here is the battery was initially connected to V volt, and then we changed it to V by 2. Same situation that we had here. Okay, this was connected to V volt. Now I did not reverse the polarity. Rather, I got another EMF. I got another cell which had an EMF of V by 2. Okay. Now, what is going to happen in this case? This one is very interesting, students. Okay. So looking at the solution out here, initially this was the condition. Excuse me. Initially this was the condition. Now, what you did is you changed the EMF to V by 2. Now, what will be the charge? I mean, when steady state has been reached, this is going to be CV by 2. If you are not able to see it, I'll just write it in bold. This is like CV by 2. So this plate had initial charge. This is interesting. These are an initial charge of CV. And now the final charge is equals to CV by 2. That means my final charge is less than the initial charge, my dear students. So here, this goes interesting here, because if my final charge is less than the initial charge, where did the charge go? Now, here in this case, the charge, in the first case, the charge was provided by the cell to the capacitor. Now here, interestingly, what happens is my battery is getting charged at the expense of the energy which was stored in the capacitor. All right, students. So if you see here, the charges are going to go this way. All right, initially, and then what do I have out here? Okay, this is like the final state. This is the final state. This is the progression of what was happening out here, and this is where we reach here finally. Then, my dear students, as you would see, yes, you can guess, I've kept these places blank. What is going to be the work done by the battery? So, difference in the charge is going to be how much? Nothing but CV by 2. The charge transferred by the capacitor to the battery is CV by 2. Now, this part is important. The charges are basically, if you see this, it is entering the positive terminal of the battery. So we are basically going from the positive terminal to the negative terminal. Students, we have seen that's a voltage drop. So what is the potential difference across which the charge is entering? It is going to be nothing but minus V by 2. Clear, students? So work done by the battery is now going to be negative work. All right, because the battery is getting charged at the expense of the capacitor. So that is like minus CV square upon 4. All right, students. So that I can write it as minus CV square upon 4. That is nothing but that is a work done by the battery. It's a negative work. Okay. And here, change in energy stored in the capacitor. What is the final energy stored in the capacitor? Let's get back to the next last slide. So U final, if you see here, right? Absolutely correct. It's like half C. What is the voltage? V by 2 whole square. All right. So if I kind of put this together, this becomes nothing but 1 divided by 2 CV square upon 4. All right. And what is my initial charge? Half CV square. Half CV square. That was my initial energy stored in the capacitor. Then, my dear students, if you have to calculate like, delta U, okay, that's nothing but if you have to calculate my change in the energy stored in the capacitor, okay, and apply it to the formula that we have just seen, my dear students, it is going to be nothing but the final charge, U final minus U initial. U final is nothing but 1/4 of half CV square. All right, so that's like half CV square. Clear? Minus half CV square, that is my initial. Clear? So definitely I can see my half CV square is kind of common. Half CV square is common. And 1 by 4 minus 1, so that's like, minus 3 by 4. Clear, students? Then getting back to this, that's like minus 3 by 4. All right, CV square, my dear students. And if you calculate the heat here, I think you have got it. You've got then, which implies your Q is equals to 3 CV square by 4 minus CV square by 4. So that is going to be 3 minus 1. That's like 2. And here I'm going to have CV square by 4. All right. So the answer is CV square by 2. All right, students. So that's like, the end of our today's session that you would call on few topics or concepts based on capacitors. I hope you've liked the problems. Okay, students, these are important concepts that have come over the previous sessions of your KVPY. All right. As much as possible, there was one question I remember. I'll just get back to that one once again. And this was one homework question for all of you. So all of you can, like, if you have not noted this question before, you can just have a close look at the question, note it down, okay, and revert back to me with the answer at the number provided out here. Okay, students. Now, besides this, I like to bring another thing to your notice. That is that we have our KVPY sessions already started, students. Now, time is less for these examinations. All right. And just after your session on, just after your KVPY examination gets over, then there we have our JEE mains examination. Then, my dear students, for this, we highly recommend students to take their KVPY revision program very, very seriously. Okay, what happens with that? You get prepared for the examination. Since we have already started, now here at Vedantu, what happens is, as I told you even at the last time, that all our sessions, they are online sessions, they are recorded sessions, okay? So there's nothing much that you would have missed. So we already have it, like, the previous session recorded. So once you kind of register for our course, all right, students, once you kind of register for our course by visiting this particular link that is being given out here, what you can do is just, like, go through the recording of the previous session, and tomorrow we have our, like, next session on Friday, and that is going to be taken by me, by your Sumit sir. All right, and we can come alive, describe, discuss a lot of problems during those sessions. And if you have any doubts, you can always get back to me through the WhatsApp groups and all that. All right, students, then good night for today. Hope you liked our session. And if you kind of liked it, do remember to like the videos. All right. And take care, and God bless you to all of you. Okay. So stay tuned and wait for the next video also. Okay. Which is going to be on electrodynamics. Okay. Fine then. Bye-bye. Take care.